Hi kids. Ran into a little bit of bad luck, so I'm not going to be with you guys today. We'll hopefully be back tomorrow. Just to give you an overview of what we're going to be doing today. First, we're going to start by checking last night's homework, and then we're going to do section 112. So we're going to start with the 112 warm-up, then go to the 112 scaffolded practice. We're just going to do example 1 today. And then with any extra time, you can work on tonight's homework, which is a 112 worksheet all about z-scores. So go ahead, take out your calendars and jot down tonight's homework. So again, in class today, we're going to be doing lesson 112, which is about our standard normal curve and all the calculations that come along with it. Homework tonight is assignment number 8, and again, it is the 112 worksheet, day 1. And just to remind you guys that at any point you can pause, replay, rewind, rewatch, whatever you have to do to make sure that you're following along. So our objectives for today, by the end of class, you should be able to understand what a z-score is, as well as calculate the z-score of a normal distribution. So if you want to go ahead at this point, take out your homework from last night, and let's go ahead, check our answers. So for number 1, we should have gotten 68%. There's a picture there, along with our standard deviations written below it. Example number 2, 97.5%. Example number 3, 1.25 minutes. And don't forget, we should be drawing a picture along with all of our examples. Example number 4, 2.5%. Example number 5, about 11.1%. Example number 6, about 27.8%, and remember those are with our uniformed distribution. Example number 7, empirical rule, so 95%. Example number 8, we end up with 81.5%. There's a little bit of my calculations in case you had any questions on that. Example number 9, with the way that the mean property value is, as well as with that standard deviation, if you take a look at the standard deviation, just the data alone, several of those are too many standard deviations above. So if you even go 3 standard deviations above at 240,000, we're not even at $1 million. So we run into some issues there, as well as if you end up drawing out the normal distribution like we have here, we end up getting standard deviations, actually 1, 2, 3, all 3 standard deviations to the left of the mean end up in negative dollar values, and that's not possible. So there's no way that that distribution could be normally distributed. All right, so let's go ahead and get started with our lesson today. So go ahead, turn to section 112, and let's start with the warm-up. So at this point, I would like you to please pause the video so that you can read through the warm-up and try the warm-up on your own before replaying the video with the answers. So hopefully you were successful with our warm-up. Here, first of all, when you see the word combination, it is the same thing as outcomes, where last year in Math 2, I know you guys did a lot with possible outcomes, all possible outcomes, etc. Combinations, outcomes means the same thing. So if we take a look at our answers, number 1, estimate the mean of the sums. So since the distribution appears to be normal, you can assume that the middle is the mean. So if we look back, we have a mean of 14. why is it more likely to roll a sum of, why is it more likely to roll a sum of 10 than a sum of 5? If you, again, look back out at the possible outcomes, if you compare 10 outcomes to 5 outcomes, it's much more likely. There's 80 possible combinations with a sum of 10 versus whatever that is, 5 possible outcomes with a sum of 5. So that's why it's more likely to get a sum of 10 than a sum of 5. What is the probability of rolling a sum greater than 20? So all you have to do is add all of those up. So if we add those up, 0.01, and this is again from the chart. So if we take a look here, greater than 20, so we're looking at these values here. If we want to add those up, because again, that row there represents the probability of getting each. Add up those probabilities, and we end up getting about 2.7%. What is the probability of rolling a sum between 10 and 15 inclusive? So inclusive means you include 10 and 15. So again, just go back to that chart. We should have looked at our probabilities between 10 and 15, added up all of those numbers that I have marked in green, and we end up getting not that. We end up getting about 56.7%. So describe the similarities and differences between the distribution of the sums of the 4 6-sided dice and a normal distribution. So clearly the shape of the distribution of dice outcomes in the normal distribution are very much alike. However, the normal distribution is for continuous data, and the dice roll is discrete, meaning that you cannot have a sum of dice to be 10.1. There's no infinite possible sums between, let's say, 10 and 11. It's either you have a sum of 10 or you have a sum of 11. So that's really the big difference between a normal distribution and this probability distribution here is the discrete versus continuous. So let's go ahead now and let's take a look at example 1. So example 1. In 2012 Olympics, the mean finishing time for the men's 100-meter dash finals was 10.10 seconds, and the standard deviation was 0.72 seconds. Usain Bolt won the gold medal with a time of 9.63 seconds. Assume a normal distribution. What was Usain Bolt's z-score? So first of all, what the heck is a z-score? Well, the technical definition of a z-score is the number of standard deviations that a value lies above or below the mean in a normal distribution. So we've actually already been writing down z-scores. I'm going to flip back a couple slides. If we take a look at the homework from last night, for example, all of the ones that we've been doing, we've been writing the calculated mean and then the calculated values of standard deviations to the right, to the left, and below it, remember we were writing those numbers 0, 1, 2, 3, which represented how many standard deviations we were away from the mean. All we were doing, we're writing down z-scores. So a z-score just tells you how far away is your data point from our mean. They're positive and negative. So if we have a positive z-score, it means that we're above the mean. Negative z-scores mean that we're below the mean. So for example, a z-score of 1.2 means that we're 1.2 standard deviations above our mean. And a z-score of, let's say, negative 2.5 means that we're 2.5 standard deviations below our mean. Now, how do we actually calculate a z-score? Well, it turns out that you can calculate z-scores with sample statistics or population parameters. Sometimes in a set of data, you won't know if you're working, if the mean that they give you is a mean of a sample or a mean of a population. But it turns out that the calculations are the same. You can find any z-score by taking your observed mean or your observed value. So in this context here, it would be Usain Bolt's time minus the actual mean divided by the standard deviation. So S would be standard deviation of a sample statistic, where again, lowercase sigma or baby sigma is the standard deviation of your actual population. So when we're doing all of these, first things first, let's draw our picture, just like we were doing the last couple of days. So let's go back up and let's treat this problem just like we did before. So we know that Usain Bolt has a, his time was 9.63 seconds, but the actual data of 100-meter dashes has a mean of 10.10 seconds with a standard deviation of 0.72. So let's sum that up. There it is. So we start out with our mean, go 1 standard deviation to the right, 2 standard deviations to the right, 3, and then same thing to the left. So we end up getting our normal distribution looking like this. And if we calculate Usain Bolt's score, it turns out that 9.63 isn't nice. It's not one whole standard deviation. So if we go ahead and fill in our z-scores like we've been doing, our mean again 0, to the right 1, 2, 3 standard deviations, to the left 1, 2, 3 standard deviations, we see that Usain Bolt falls somewhere in here, 9.63. So again, we don't know what that z-score is because it doesn't fall on a nice standard deviation. But we know that it's going to be a negative standard deviation because his time is to the left of our mean. And we know that it's not going to be quite one whole standard deviation to the left, just based on where that point falls. 9.63 is not quite 9.38. So that's why we're going to go ahead and use that formula. So either one of these is fine. I'm going to go ahead and use our sample statistic one. Our z-score, again, we get by taking Usain Bolt's time, 9.63, minus the mean of the 2012 Olympics, divided by the standard deviation. So if we look at our data, substitute those values in, we get z equals 9.63 minus 10.10 divided by 0.72. So we end up getting a z-score of about negative 0.67. Now, careful when we're putting this into our calculator that we don't make some mistakes. So how we should be doing this is, well, if we decide to make this 2 steps, we should do the numerator first, find our answer, and then divide by our denominator. If you put it in your calculator like this, remember order of operations. So your calculator is going to first divide negative 10.10 by 0.72 and then do 9.63 plus that value. So if we wanted to fix this, we would just have to add a set of parentheses. Right here. And then we would end up getting that same answer. Now, this is going to be super helpful because in tomorrow's lesson, we're going to learn how to use that z-score to then calculate probabilities. So we can then take this example and find out how many people in the past have had faster times than Usain Bolt, if any, how many people did he finish faster than, etc. And be able to answer a whole bunch of different types of percent problems, similar to what we've been doing the last couple of days, just not when it falls on an exact standard deviation. So that's it for today's lesson. At this time, you can grab your homework from the sub and you have the rest of the period to work on it. I will see you guys tomorrow.